So my name's Sam Garner, if you haven't met me before. Previously, we've talked about sand reclamation, we've talked about mold automation, but today we're going to talk about robotic sand milling. So a little bit different. It's not new technology, as we know, but let's talk through it. I don't know if it's working on the space, is it? It was not. There we go. Tough space bar. Right, okay. So robotic sand milling. So the RSM is an efficient, cost-effective solution for moving into a patternless mold-making system. It's an alternative to 3D printing molds, or it's used in combination with 3D printed cores. The two together is the ideal solution. But the RSM cell was first of its kind to be developed and marketed by a well-known foundry equipment supplier or manufacturer. While other robotic integrators have produced milling cells, none of them have been created specifically for sand molding and machining as its first priority. So this means that more important aspects of the process, such as mold handling and tool wear, for example, are prioritized. But it utilizes a 6-axis robot combined with a software that's also designed from the ground up with Foundry mold milling as its primary focus. This enables a combination of easy operation, design flexibility, cost savings, and speed compared to other prototype or short-run methods. But what is robotic sand milling? So robotic sand milling is a process where a robotic system is employed to mill or shape sand molds. A robotic arm is equipped with milling tools and is programmed to precisely remove excess sand from the mold to achieve the desired cavity or shape. The robot follows a predetermined path based on CAD data of the mold, ensuring accuracy and repeatability. Obviously, there are advantages to this. So the advantages are precision and consistency. The system can achieve high precision and consistency in milling sand molds. Obviously, following that program path with minimal deviation, resulting in accurate mold cavity, leading to consistent castings. We can also do complex geometry. So the RSM being multi-axis means it excels in handling intricate designs, undercuts, and complex shapes, unlike traditional patterns, which are obviously limited. But it's perfect for development and prototyping. You can also use it, so runner systems that may not be feasible, for example, with traditional molding, can be milled into the sand mold. Molds made from multiple pieces to create undercuts, such as propellers, can be milled, saving extensive molding times and potential defects, such as sand inclusions. It also saves time, material and tools. A basic shape can be molded into the sand block to save on materials, but you can start with a basic cavity in the sand mold and add features. This cuts down on waste material and obviously milling time. And it's fully automated, so once the mold is located in the cell, the system can run hands off from start to finish. The setup, we set the machine up, we let it run overnight, and you come to work in the morning with a finished mold. There are obviously benefits over traditional pattern making, so there's no more patterns. So this bypasses the need for traditional patterns. So it greatly reduces the costs and lead times, which are normally associated with no-bake molding and the production of patterns. Space saving. So there's no need for physical patterns. The digital designs, which directly translate into a milled mold, they don't require any space, except maybe for a USB, for example. But this streamlines the production process, reduces lead times, and eliminates storage space for patterns. We can easily mill zero taper, undercuts, and overhangs. We can quickly adapt to design changes as well, so modifications can be implemented instantly. So when the design modifications occur, the RSM can adapt swiftly Simply update the CAD model, re-upload it to the CAM software, and the robot adjusts its milling path accordingly. So this agility is crucial for changes in the design process. And we can re-mill the mold. So if we need to make a change, we can put the pre-milled back into the robotic sand miller and then re-mill the mold. The benefits of this process are especially profound with large, low production castings or legacy parts. But benefits over 3D printed sand molds. So this system works with any type of resin and sand. So milling cutters, they do not care if you're cutting silica, chromite, zircon, olivine, for example. Customers can use their existing equipment just to produce a blank molds and then introduce it to the robotic sand miller. An average milled sand mold will cost approximately 1/4 of a 3D printed mold. We're talking about a full printed mold, not a core. And it's faster to produce large molds compared to 3D printing. So it can be up to 5 times faster for large molds, depending on the geometry that we want to mill. So for example, a 2 meter by 2 meter mold will approximately take about 6 hours of milling, and that's approximately 5 times faster than the printer working at about 100 liters an hour. And the RSM cell itself will typically cost less than a 3D sand printer as well, and it's typically about half the price. You see 2 pictures here, one's architectural, and you can see there's a propeller there as well, small propeller. But sustainability and cost efficiency, so there's less process waste from short run and legacy parts, so no permanent pattern. So traditional pattern making involves material waste. This could be down to pattern wear, adjustments, and scrap. The RSM minimizes waste by directly milling the required shape and optimizing that material usage. So users can use customers' existing sand system, which we already mentioned, and machine removed sand is reusable back into the mold making process. So we can reclaim that sand and then reuse that sand once it's been milled. It reduces time during prototyping and design iteration, which leads to more efficient product development. And although the initial setup cost for a robotic sand system exists, the long-term benefits outweigh them. And also reduces costs in making new patterns. Other advantages are there's a reduced labor, material savings, faster production cycles, which all contribute to an overall cost effectiveness. But the RSM, so in general operation, the RSM allows users to take a 3D file of the mold that they want to produce. So after loading that 3D file or 3D model of the mold, a large array of toolpath types and methods can be used to ensure the cutting is done exactly as it needs to be. It utilizes a full 5-axis suite of MasterCam for program toolpaths. This gives us a direct line from CAD model to CAM program. So we can also review the program paths inside the software, watching stock being removed in real time to help optimize the operation. So we don't have to mill the mold. We can see it on the computer. We can see it happening live before we then put it into production. Once the toolpaths are finalized in MasterCam, the operators transfer the mold program into Robot Master at just a click of a single button. But inside Robot Master, the motion of the robot can then be observed, as you mentioned, and adjusted as it moves along its toolpaths. This is a critical ability for avoiding issues such as singularities, joint limits, and as well as general collisions inside the cell. And also, and then once reviewed, the RSM can begin to mill directly into the standard no-bake sand block or mold. But Robot Master clearly defines any issues and helps offer easy-to-use tools to find the solutions that we need. Users can also take benefit from automatic path optimization, which can be geared towards either smoothness or avoidance, or error avoidance, or any combination of the two. But MasterCam and Robot Master. So MasterCam is the CAM package, which is for toolpath programming. We can use other CAM packages instead. So if a Foundry or customer already has a a license with a CAM provider, we can use that to, for example, Autodesk or PowerMill. Now, although MasterCam is a recommended software because it has been developed with Robot Master, but Robot Master acts as the translator between the CAM package and the robot. So it basically takes the G-code program that gets output from MasterCam and then converts that into the robot language file. The robot then understands that and can move along its toolpaths. But the RSM can operate 24/7, which enhances productivity. Robots don't tire, take breaks, require shifts. They constantly produce molds, when they're set up correctly, which contributes to higher efficiencies. But Richard might like this one. Also, robots handle hazardous tasks such as sand milling without the risk of human safety. This reduces workplace accidents and ensures a safer environment for Foundry worker. Okay, so just to go through, this is MasterCam and Robot Master as a side-by-side. This is the first stage of production. We then move to a 3-point calibration. The operator simply locates the mold using a 3-point touch-off. We then measure the length of tooling which will be used, and we load that into the tool changer. So you can see on the left-hand side, we're measuring the length of the tooling, and then we're integrating it into our tool changer. Once the operator confirms the setup, they hit execute. The robotic arm will then select the appropriate tool, ensure it is within its wear tolerance before starting the toolpath. So that wear tolerance can have a huge effect on how much we're milling. If we're under spec, we're not taking as much material away. But once it's confirmed, it's within that tolerance, the operator can walk away while the cell runs through all its toolpaths from start to finish. And then there we have a robot just about to mill the mold. And hopefully the video works. But this is the full cycle. Obviously, this is sped up. We can't mill molds at this speed. But you can see we have a hydraulic tilt table which presents the mold vertically to the robotic arm. A 3-point calibration to 3-point touch off. The robot selects a tool from the tool changer. Typically, we have two holders of 8, which 16 tools in total. And we first go through this first stage is the roughing phase. So we can use a tool here that's maybe been used as a finishing stage. We don't need that. We don't need that fineness yet from the finishing. So we're taking away a lot of material here. Checking the tools to make sure they're still within tolerance. And now we're doing the finishing stage. So this is where the accuracy comes in. And that's the casting. That was cast after we milled the mold. So we go through design, interface. So we have the operator interface into a blank mold, into the milling stage, and then through that milling stage, we change tools, and then we have the final milling, the finishing stage. But surface finish. So the surface finish will be down to the size of the grain that's basically used. The finer the sand, the better the finish. So you can see we've got a pretty good finish on this picture anyway. There's not much difference, if any, with whatever process that we're using. So alkaline, phenolic, Pepset, for example, there's no difference in surface finish. The harder the resin system, it could mean faster wear on the tooling, but there's no evidence that currently supports that or shows that. But edge definition as well. You can see from the picture, they're quite sharp edges here. So the RSM is limited by the diameter of the cutter that's being used. Because it's a rotary cutter, there will always be a radius to any corner. So similar to a CNC machining center, for example. But for the areas that would need to have perfectly square, like a corner for chills, we recommend using a small, as small as possible cutter for the finishing passes. But the tools used, so generally the best cutter material is a regular carbide, end mill or insert cutter. There has been testing done which compares diamond coated tooling as well as high speed steel cutters, but for the cost difference, it did not make much difference in terms of increasing that tool life. But tool wear lifespan is also greatly dependent on the geometry being cut. Generally, a new end mill would be usable for finishing passes for 8 to 10 hours of cutting before getting worn, and the limit of the holding tolerance obviously decreases. But at that point, that tool can then be demoted to the roughing only. So we're getting as much out of that tool as possible. Depending on the acceptable levels of wear, it could be used for another 8 to 10 hours before then being scrapped. The system components themselves. So the system comprises of 6 core components, which create almost the backbone of the system. These components ensure seamless operation, integration for automatic mold milling. But the RSM22, so it has a cell control system. This is a B&R industrial PC-based control package. It has a toolpath selection page, which allows for fully automatic operation from first toolpath to the last. Also, it has a tool data logging, which keeps track of tool usage in minutes and tool wear as well. So when combined with the optional laser micrometer, we can combine the two and keep track of that. Obviously, the 6-axis robot, you can see here, we use ABB. This one's an older version with a KUKA robot. It has a maximum reach of 3.2 meters and has an AA specification accuracy. So I think that's down to 0.04 inches. So accuracy is pretty high. A high-speed spindle. So the spindle works with the automatic tool changing system. It's a 13 kilowatt spindle. The dual tool change stations as well hold up to 8 each and has a fully covered design. It also has an integrated pneumatic nozzles, so with a cleaning tool. So every time the tool is in there, before it gets picked up, gets cleaned, so we don't get any dust in the tool. The CAM program package. So as we mentioned, the Master CAM and the Robot Master, and the mold clamping table. So on this picture here, you can see this is a hydraulic tilt table, which allows us to bring the mold up vertically to face the robot. The advantages of that is because we're milling vertically, the sand is falling away from the mold. If we mill horizontally, the sand stays in the mold. So we're constantly the sand is still there, and we're decreasing that life of the tool. There is another option. You can use a manual clamping station. So if you have the advantage of having a manipulator, for example, you can manipulate the molds, put it onto the table, clamp it up. As long as we can locate the mold, we can use it. There are expansion. We can expand the capabilities by introducing further options. So we have multiple mold tables per cell, which allows for simultaneous setup and milling. Multiple robot cells per control system, so we can have multiple robots with a one B&R system. As it says, it can be run from the same cell control software system. The tool inspection station, which is not an optional extra, we can increase the spindle to a 30 kilowatt spindle. So this increases the speed of milling. So for the roughing phase, not really for the finishing stage, but for the roughing, we can speed up that process. And we can also add a 7th axis, which is a horizontal gantry. So you can see a picture of that on the right-hand side. And that is to allow us to increase the size of the mold to 4 meters by 2 meters. So it's quite a large mold, and the robot will run along that track and carry on as milling. But these options give us adaptability and efficiency to the system. This is just a general example of a layout of the robotic miller. So you can see the arm at the back end here, hydraulic tilt table, and the mold being brought to the face. We have two main sizes. The RSM 22, which is a 2 meter by 2 meter by 1 meter mold, and a 42, which is the 4 meter by 2 meter mold with the 7th axis gantry. But in summary, the robotic sand miller offers a paradigm shift into Foundry practices, which combines precision, quality, adaptability, control, and efficiency. And this ties in with our values to provide options for all foundries as we move into automation and a modern manufacturing landscape. And thank you for listening.